Hello everyone. In this video I will teach you a important derivation deals with the Pelton wheel turbine. So the question is, show that the maximum hydraulic efficiency of Pelton wheel is equal to 1 plus cos phi divided by 2, in which phi cannot be equal to 0 for increasing efficiency. So we need to prove that the maximum hydraulic efficiency that we are getting from the Pelton wheel turbine is equal to 1 plus cos phi by 2. So now for proving this, we want to draw the velocity triangles for the turbine. So let us draw this. So let us consider, so this be the inlet velocity triangle that is drawn at the inlet tip of the bucket, that is exactly at the splitter point. So this is how the bucket shape look like. So the center point of the bucket is said to be the splitter. It is named as splitter because at this point the jet will be splitted into two parts. Half of the portion will comes above and half of the jet portion comes in or moves towards the downward direction. So now, so the inlet of the velocity triangle look like this. So here u1 represents the velocity of the wheel at which it is moving. Vr1 represents the velocity, that is the relative velocity of the jet that is travel and which is getting exactly hit at the splitter point. And then V1 represents the absolute velocity that is traveled by the jet. Similarly, Vw1 represents the velocity of the wheel at the inlet of the jet. So in this case, both V1 will be equal to V1 will be equal to Vw1 here. That means the absolute velocity that is traveled by the jet will be equal to the velocity of the wheel, because we are not getting the angle here. Here the angle alpha is 0. So that means the jet is exactly coming in the radial direction towards the splitter. So now this is the inlet velocity triangle which is for the Pelton turbine. Similarly, the outlet velocity triangle look like this. So in the outlet velocity triangle, here the angle beta is the angle which is made by the absolute velocity with the vertical direction. So now the absolute velocity here is V2 and VR2 represents the relative velocity at which the jet is leaving the splitter, and U2 represents the velocity of the bucket at the outlet tip. Similarly, VW2 represents the velocity of the wheel at the outlet tip, and VF2 represents the velocity of flow at the outlet. Now this is how the velocity triangle look like in the Pelton wheel turbine at the outlet of the bucket tip. So now with respect to these two velocity triangles, we had to derive the equation of hydraulic efficiency. So let us start deriving this. So for deriving, let us consider the inlet velocity triangle first. So now from the inlet velocity triangle, we can write VR1 as VW1 minus of U1. So let us write this as VR1 is equal to VW1, which is nothing but your V1 itself. V1, that is absolute velocity, minus of U1, that is velocity of the bucket. So that gives you the equation for VR1 and name the equation as equation 1. So here, so whatever the velocity of the bucket that is moving once the jet hits the splitter, with the same velocity the bucket will move at the outlet tip. So that means U1 will be equal to U2. So which is equal to U. We can name this as finally as U, because the velocity at which the bucket is moving on the inlet tip will be as same as the outlet tip. So for that reason we can keep U1 as equal to U2, which can be equal to U. So now let us replace this U1 with U here, and let us write our final equation for VR1 as V1 minus U and name it as equation 1. Then now let us consider the second velocity triangle that is acting at the outlet tip of the bucket. So now in this triangle, so we have to refer the outer triangles, that is the bigger one. From the outer triangle, this is the angle of phi that is making at the other end of the triangle. So here If we apply cos for this triangle, the cos phi will be written as adjacent side to its hypotenuse. So the adjacent side for the angle phi is u2 plus vw2, then divided by its hypotenuse is vr2. Hence, cos phi will be written as u2 plus vw2 divided by vr2. Now here I want the equation of vw2. So let us cross multiply this. On cross multiplying we get vr2 into cos phi is equal to u2 plus vw2. But I want equation of vw2 here. So for which I will be keeping vw2 as it is and I will be bringing this u2 to the other side. If I bring plus u2 to other side, that will become minus, hence the equation of vw2 will be written as vr2 cos phi minus of u2. But we know that the relative velocity at which the jet is striking the plate at the splitter will be equal to the velocity of the jet that is leaving at the outlet tip. So for that reason, VR1 will be equal to VR2. So now let us keep this equation now. The equation of VW2 we got it as VR2 into cos phi minus of U2, and let us replace this VR2 with VR1 because the relative velocity of the jet both at the inlet as well as the outlet will be same. Now on replacing VR2 with VR1, we will finally get the equation of VW2 as VR1 cos phi minus of, you replace this U2 with U. Hence, we get the equation as VW2 is equal to VR1 cos phi minus U, and let us name this as equation 2. Now, from the first equation, we have VR1 is equal to V1 minus U. So, let us replace VR1 with the first equation in this equation 2. On replacing VR1 with V1 minus U, we will get the equation of VW2 as V1 minus U of cos phi minus of U. Let us name this as equation 3. Once we get the third equation, let us find out the equation of force which is generated in the horizontal direction. Now the force which is exerted by the jet of water in the direction that is moving in the series of the curved vein is given by Fx. So the formula to find Fx is mass per second into change in velocity. So here change in velocity is written as initial minus final velocity. So now rho a v1 gives you the mass per second of water here, and the initial velocity is the velocity of the water at which it is moving. Initially the water or the jet is moving with a velocity of Vw1, which will be moving in the rightward direction. Let us take this as plus Vw1 minus of final velocity. So now the final velocity that is traveling by the jet at the outlet tip is Vw2, and that will be usually moving in the leftward direction. As it is moving in the opposite direction, let us take it as minus. So minus of minus gives you plus. Hence the final formula for Fx we will get it as rho a v1 into Vw1 plus Vw2. So that is the equation of force which is generated by the jet in the motion of the series of the curved vanes. Once we get the equation of Fx, let us find the equation of work done by the jet. So we know that work done per second is given by the product of force with its displacement. So here force is Fx and displacement is the velocity of the plate here. So now we got the equation of Fx as rho a v1 into Vw1 plus Vw2. Let us write it the same equation in the next step and multiply the equation with U. And let us name this as equation 4. Now in the next step, let us substitute equation 3 in equation 4. See, in the equation 3 we got the equation of Vw2. We have the term Vw2. Let us replace this term with the equation V1 minus U into cos phi minus U. So let us equate 3 in 4. On equating 3 in 4, we get work done per second as rho a V1 will remain as it is into Vw1 remains as it is, plus of, in place of Vw2, we will be replacing that with V1 minus U into cos phi minus of U. Let us replace it and multiply the whole equation with U. Now, we know that we have already kept VW1 as in terms of V1, so no need of converting this V1, but we know that VW1 is V1. Let us keep this VW1 as V1 in the next step. Now, in the next step will be written as rho A V1 into, replace this VW1 with V1, we get V1 plus of V1 minus U of cos phi minus U whole multiplied by U. See, you are having the term V1 minus U. Let us keep these two terms as single term, that is V1 minus U, plus of the remaining V1 minus U of cos phi you need to write here, multiplied by U. This term will be written as it is. So, this is the final equation for work done per second of Pelton wheel turbine. Now, if you still want to simplify it, means let us take V1 minus U common from these two. On taking V1 minus 1 common from this, we will get the equation as rho A V1 into V1 minus U will be taken common. So, if we take common, the remaining will be 1 here, plus from this the remaining is cos phi into U. So, this is the equation of work done per second. So, we are deriving the equation of the hydraulic efficiency. So, let us write the equation of hydraulic efficiency now. Hydraulic efficiency is generally represented with, it is the ratio between runner power to the working power of the shaft. So, now the runner power itself represents your work done per second by the turbine, and working power is nothing but your kinetic energy of the jet. So, let us write the work done per second what we got at the last step. From the previous step, we got the formula for work done per second as rho A V1 into V1 minus U into 1 plus cos phi of U divided by kinetic energy of the jet is given by the formula half into rho A V1 cube. Now, in this equation, we have the common terms as rho A V1. Let us cancel those common terms. After cancelling, our equation will be written as denominator by denominator goes to the numerator, hence 2 comes in the numerator place, into the remaining is V1 minus U into 1 plus cos phi into U, that divided by V1 square. So, this will become the equation of eta H. Now, so in this equation, so let us multiply U with this term. So, on multiplying U with this term, we get V1 into U gives you V1U, minus of U into U gives you U square. So, remaining term will be written as it is. 1 plus cos phi will be written as it is, and 2 by V1 square has to be kept as it is. So, now name this equation as equation 5. So, that gives you the equation of hydraulic efficiency. But now, as we are deriving for the maximum efficiency, so now for getting the maximum efficiency, we need to differentiate this equation with respect to U, and at the same time the differentiation of hydraulic efficiency with respect to U will be kept it as 0. So, after differentiating, we need to equate our equation with respect to 0 here. So, let us start differentiating it. So, differentiation of above equation will be written as d by du of 2 by v1 square into v1 u minus of u square into 1 plus cos phi is equal to 0. Now, on differentiating, this is the constant term. Just keep the term as it is. 2 by v1 square will be kept as it is. So, differentiation of v1 u with respect to u gives you v1. Minus of differentiation of u square gives you 2u into, again this is the constant one, keep it as it is, 1 plus cos phi is equal to 0. Now, let us go on simplifying this. So, as we are doing for the maximum efficiency, we had to take 2 by v1 square into 1 plus cos phi as single term. So, if you take this as single term and the second term as v1 minus u, so wherever you have the term phi, there you cannot equate the term to 0. If you equate that to 0, you will not get the efficiency at the end. The whole equation will become 0 here. So, now we just can't take 2 by v1 square of 1 plus cos phi is equal to 0. If this is not 0, then what will become 0 now? So, we can take v1 minus 2u as 0. So, let us take this. So, let us take the second term of our equation and equate it to 0, that is v1 minus 2u is equal to 0. Now, on simplifying this, if I bring minus 2u on the other side, it will become plus 2u. Hence, the value of v1 will be equal to 2u. So, let us name this as equation 6. Now, what do we have to do? We need to equate this equation 6 in the equation 5. So, let us equate. So, let us write down the equation 5 once again. Eta h is equal to 2 divided by V1. So as you are having V1 term here, let us replace that with 2u. So that will become 2u square into V1 into u. So you replace V1 with 2u. 2u into u gives you 2u square minus u square, you keep it as it is, into 1 plus cos phi, keep it as it is. Then let us start simplifying this. On simplifying, we get 2 divided by 2 square gives you 4, u square you will get here, then into 2u square minus u square gives you u square into 1 plus cos phi. So here u square will get cancelled, 2 will get cancelled with 4, the remaining is 1 by 2 into 1 plus cos phi. So therefore, now we can get the maximum efficiency as 1 plus cos phi divided by 2. Hence it is proved.